Today, everyone, we would be talking about linear and nonlinear application of op amps or operational amplifiers. We are the group one, and I will be the first to report today. My name is Caris D. Chicote. So, for our first slide, we have operational amplifiers or op amps once more. Op amp can be used as a signal amplifier to increase the amplitude signal. Here we have our examples, and here it is an image of our IC and the schematic circuit symbol of our amplifier. So we have here the inverting out input and the non-inverting input, which is the negative and the positive, plus the positive voltage 5, which is called the positive voltage supply, and the other one under it is the negative voltage supply with our voltage output. Next slide, please. So first, we're going to talk about our differentiator. A differentiator is an electronic circuit that produces an output equal to the first derivative of its input. In the circuit, the non-inverter input terminal of the op-amp is connected to the ground. That means 0 volts is applied to its non-inverting input terminal. So if a non-inverting input terminal is 0 in voltage, then the inverting terminal would be also 0. So here we have input voltage, which is Vi, and output voltage, which is Vo. So the figure depicts inverting op-amp differentiator circuit. So the operational amplifier functions as differentiator when input resistor is replaced with capacitor, which is the letter C there, and the feedback resistor is not changed. The equation for the differentiation of amp is mentioned. Here, VIN is the input voltage to the op amp, and V out is the output voltage from the operational amplifier. So the formula would be VO is equals to negative RC and the derivative of voltage input with respect to time. So the output voltage again is the VO is having the negative DT sign, which indicates that there exists a 180-degree phase difference between the input and the output. Next slide. So we have here our waveforms of differentiator. So the input waveforms and the output waveforms. So that's the image and the samples. Next, please.
So my name is Rafael Gumadan. So for the integrator, so an integrator is an electric circuit that produces an output that is integration of the applied input. In the circuit, in the non-inverting input terminal of the op-amp is connected to ground. That means 0 volts is applied to its non-inverting terminal. So man siya ang ground niya, inverting terminal o output niya. So if non-inverting input terminal 0 volts, then inverting terminal also be 0 volts. So here is the input voltage or BI, output voltage which is BO, and here's the formula. BO equals negative 1 VI dt RC dVi RC over RC. So the output voltage BO is having a negative sign, which indicate that there exists a 180 phase difference between the input and the output. So, inverting amplifiers. So an amplifier which introduce a phase shift of 180 degree between input and outputs called inverting amplifier. So from the circuit, the potential node BB equals 0. So from the circuit, the lagi from BB. So from the concept of virtual ground, the two input terminals are at same potential. Therefore, the potential at node ABE equals BB equals 0. So muna siya ang BO, formula niya BO equals negative RF over R1 BIN, which inverting. So muna siya ang samples. Then waveforms of an inverting amplifier. So ano siya ang yang look like kung ato na siyang i-draw. So next reporter.
So, good morning. I'm Legaspi Memory, and I will be the reporter for the non-inverting amplifier. So, non-inverting amplifier is an amplifier which amplifies the input without producing any phase shift between input and output is called a non-inverting amplifier. So, the figure at the left side shows a non-inverting amplifier using op-amp. So from the circuit, the potential at node B, VB, is equals to V input. So from the concept of virtual ground, the two input terminals are at the same potential. Therefore, the potential at node A, VA, is equals to VB, is equals to V input. So the formula would be VO is equals to 1 plus RF over R1 times V input, where 1 plus RF over R1 is called the gain amplifier. So next slide, please. The figure below shows the input and output waveforms of an inverting amplifier. Next slide, please. So applications of op-amp differentiator. And integrator. So first, differentiating amplifiers are most commonly designed to operate on triangular and rectangular signals. So differentiating amplifiers are frequently used to process triangular and rectangular waveforms. So they can calculate the rate of change, which is particularly useful in applications involving these types of signals, such as tatong pulse width modulation. Is differentiators also find application as wave shaping circuits to detect high frequency components in the input signal. So, differentiators serve as wave shaping circuits by highlighting and amplifying high frequency components in the input signal. So, this makes them valuable for applications where you need to focus on or detect fast changing features in a signal. And lastly, the integrated circuit is mostly used in analog computer, analog to digital converters, or the ADC, and wave shaping circuits. So, next slide, please. Um, Clippers. A clipper is an electronic circuit that produces an output by removing part of the input above or below a reference. The output of a clippers will be same as that of the input for other than the clipper part. So, a clipper is an electronic circuit that modifies an input signal by removing, or the word clipping, a portion of it above or below a specific reference level. So there are two types of clippers, the positive clippers and the negative clippers. So first, for a positive clipper, it removes the parts of the input signal that are above the reference level, allowing everything below the reference to pass through unchanged. For a negative clipper, it removes the portions of the input signal that are below the reference level, allowing everything above the reference to pass through as is. So, Francis Enriquez will further discuss the positive and negative clipper.
Good morning. So, a positive clipper is a clipper that clips only the positive portion of the input signal. So, uh, the illustration here shows that in this circuit voltage, signal Vi is applied to the non-inverting terminal of the op amp. The value of the reference voltage Vref can be chosen by varying the resistor. So there are two cases for this clipper, for this positive clipper. So first is if input voltage is less than the reference voltage, the diode or D1 behave forward bias. So VO is equal to V1, VI rather. The next case is if VI is greater than Vref, the diode D1 behave reverse bias. So VO is equal to Vref. Next, please. Lastly is the negative clipper. So it is a clipper that clips only the negative portion of the input signal. In this circuit voltage signal, VI is applied to the non-inverting terminal of the op-amp. The value of their reference voltage Vref can be chosen by varying the resistor. So it also has two cases. So first is if Vi is less than Vref, the diode D1 behave forward bias. So Vo is equal to Vi. Lastly, if Vi is greater than Vref, the diode D1 behave reverse bias. So Vo is equal to Vref. That's all.
Good morning, sir. My name is Ivan Ibanez. So next is clampers. A clamper is an electronic circuit that produces an output which is similar to the input but with a shift in the DC level. So there are two types of clamper, which is first is positive clamper and second is negative clamper. A positive clamper circuit outputs a purely positive waveform from an input signal. It offsets the input signal so that all of the waveform is greater than 0 B. A negative clamp is the opposite of this. This clamp outputs a purely negative waveform from an input signal. Next, positive clamper. A positive clamper is a clamper circuit that produces an output in such a way that the input signal gets shifted vertically by a positive DC value. In the circuit, the AC voltage signal is applied to the inverting terminal of the op-amp. The DC reference voltage Vref is applied to the non-inverting terminal of the op-amp. The value of reference voltage Vref can be chosen by varying the resistor R2. In this case, we will Vref of a positive value.
So, good morning. My name is Margib Sipolse. So, to continue, negative clumpers, uh, it's a, negative clumpers is a circuit that produces an output in such a way that the input signals get shifted vertically by negative DC value. So, in the circuit, the AC voltage signal is applied to the inverting terminals of the op amp. So the DC reference voltage or Vref is applied to the number no inverting terminals of the op amp. The value of reference voltage Vref can be chosen by varying the resistor R2. In this case, we will R Vref of a negative value. So as we see in the figure kanang nasa picture kanang kwan is wala example sa negative dampers. So next by. So we form a positive and negative clampers. So in the left side, we see that ang waveform sa positive clampers is the clampers circuit produce an output in such a way that the voltage signals Vi gets shifted vertically upward by the value of Vref. So as we see kanang nas pabaw kay kuha na siya mao na siyang easy signal sa positive clampers. Then ang nasa ubos is positive signal sa DC signals sa positive clampers. So as we see ang yang DC signal is ni-shifted siya pa upwards while ang negative clampers is the circuit produce an output in such a way the voltage signals Vi gets shifted vertically downwards by the value of Vref. So as sa AC nga signal is mao gapon siya nasa sa center then pagabot na sa DC kay ni downwards iyang ni shifted to downward siya. So mo nang waveform sa positive and negative clampers. So thank you.